Okay, so let's get started. Let me share my screen. Everybody, can you see my screen?
Yes, sir.
Yeah, the
Yes.
chapter title is Frequency Response. So this is the new chapter, and as I said, this is very important chapter. Um so the frequency response, of a circuit is the variation in its behavior with change in signal frequency. This means that, like, you have a circuit, and if the frequency changes, for example, here the frequency is 60 hertz, but if the frequency goes higher, then what? Then how does the circuit behave? That is the frequency response. And that is very important. Here I have written in terms of application that frequency has a lot of application in communication, control system, any navigation system, aeroplane system, a lot of industrial control system. So therefore, frequency response is very, very important. Now, with regard to that frequency, when we'll be learning frequency, several concepts are of high importance. For example, one is filter. And then there is one thing, it is called the resonance. And with regard to series circuit, it is called series resonance. With regard to parallel resonance, it is called parallel resonance. Then one important term, it is called quality factor, then body plot, and scaling factor. So we will be looking all of those things. So today mainly we will be covering that filter. So therefore let's have a look that what is that filter, and there are several types of filter that we'll be looking. And that filter is the one branch of frequency response. Uh, Everybody see this slide. Here you see. So I think you all know the term filter. Even currently, I think many of you are learning electronics course 3211. There you might have covered the filter. So filter means it's a circuit that is designed to pass or allow signals with desired frequency and reject or attenuate others. This means that filtering means like you are choosing a specific band or a specific signal with a desired frequency, and you are not allowing the others. Then the best example is that, for example, like when you are driving your car and then you want to listen to radio, and then okay, I want to tune this band or that band, like 900 megahertz band or 97 megahertz band, and that is the like Memphis channel or other city channel. So basically that means you are filtering. By selecting, you are filtering. You are going to a particular frequency signal, and you are not allowing the other signal. That is called the filtering. So therefore, that filter basically two types. One is called passive filters, and other one is called the active filters. So passive filter means these filters consist of those common passive elements like resistors, capacitors, and inductors, which is called the passive elements. And active filter means those filter will have active elements like transistors and op-amp, operational amplifier. So I believe you all have studied about operational amplifier in circuit analysis on course, in DC circuit course. Therefore, when in a filtered circuit, you will have transistor and operational amplifier in addition to those passive elements, then you will be calling the active filters. So therefore, it depends on the application. Some cases passive filters are enough. In some cases, you need those components plus the advanced component like transistor op amp. Then you will call it active filters. The efficiency will be high, system gain will be high. It depends on the application. So gradually we will be looking all of those things. Now, Passive filters are again the four types. One is called the low pass filter, high pass filter, band pass filter, and band stop or notch filter. Therefore, uh, for example, I have written low pass filter means it passes low frequencies and stops high frequencies. So high pass filter means it will allow high frequency, but it will stop or reject the low frequency. And then band pass means it passes frequencies within a frequency band and blocks or attenuates frequencies outside that band. And band stop or notch filter, they passes frequencies outside a frequency band and blocks or attenuates frequencies within the band. So to understand, let's take you to the whiteboard. Let me draw for you, then it will be clear to you. Just a moment. Okay, so everybody see. So because we are looking the frequency response, and then in last class we learned about the transfer function. So when you have a circuit, then for that circuit you will have the transfer function. But you have to express that transfer function. Typically it is expressed by symbol H. So it will be the function of omega, because you know that omega means that is the 2 pi f. So the frequency is involved in the omega. Because in the frequency response, we are looking the variations of frequency, effect of change in frequency on the output response of the circuit. That's why for any circuit, you have to know what is the transfer function in terms of omega. So then because inside omega there is frequency, that's why you have to know the transfer function. Now, for example, you calculated the transfer function for a circuit and then you want to plot it. You want to look it that here it is omega and here it is that on that function, transfer function. So this means in this axis I am plotting the omega that which is proportionate to that frequency, and here transfer function. Now we learned couple of terms that, for example, first one we look the low pass filter. We call it low pass filter. So how does it look like? So the low pass filter means it will allow the low frequency. For example, this is the zero frequency, and up to a certain frequency, omega c, it is called the cutoff frequency. Let me write down that. It is called the, sorry, it is called the cutoff frequency, this point. So this means that for the low pass filter, it will pass until a certain point. This means basically it will allow or it will pass only the low frequency. For example, 0 to until this point, and after that it will not allow. That is why it is called the low pass filter. Similarly, when it is the high pass filter, it will look like that. For example, again in this axis your frequency omega, and here it is your transfer function. You are plotting or you are looking it. So this is your zero position. You see, this means what is happening this one? In this case, at the beginning it is not allowing, but after a certain point, again it is called omega c, cutoff frequency. From that it is allowing. Actually, it will not be. Sorry, it will not be blocked. It will be like that. It will go in that way. So this means that it will not allow to pass the low frequency, but it will allow to pass the high frequencies. Starting from this point, it will allow any frequency. Accordingly, it is called high pass filter. So this is the example of high pass filter. Now there was the band pass filter. There is other type. Let me write here. It is called the band pass filter. So what is that bandpass filter? Bandpass filter look like, sorry, let me draw it here. Again, so always in this axis omega and in this axis my transfer function. So when I am plotting that one, so bandpass filter is like that. You see, this is your omega 1, this point is your omega 2. So meaning that, look, it is not allowing anything between 0 and omega 1 frequency. Again, it is not allowing anything after omega 2 frequency, but it is just allowing a certain band, only this range of frequency. Accordingly, it is called the band pass filter. And then there is other type. It is called that like band stop, or it is called the notch filter. So how does that look like? Look here, so everybody. Again, it is omega here, and here that my transfer function, and sorry. You see, so this means this is your 0 position. This is your omega 1, this is your omega 2. Look, initially it is allowing until omega 1, 0 to omega 1. Then it is not allowing this band. Between omega and omega 2, it is not allowing anything. And after omega 2, again it is allowing. So therefore, this portion is actually called the stop band or the band stop. And because it is creating a hole or the notch, accordingly it is called the notch filter. So therefore, these are the main 4 types. Like this one was the low pass filter. It is passing the low frequency. This is called the high pass filter. It is allowing the high frequency after a certain point. This is allowing only a specific band. Only this zone is allowed. Before that point, after that point, it is not allowing or it is rejecting. Similarly, this one, it is not allowing anything. In this specific band, in the specific zone, it is blocking everything. But before that point and after that, it is allowing everything. So therefore, these are the main 4 types. Now, definitely you can understand, because I am plotting the H omega versus omega, what is my circuit that will represent these characteristics. Similarly, how does the circuit look like so that it will behave like that? And what is the circuit for this? And what is the circuit for this? So today I will show you those circuit, and we will be calculating the transfer function, and then we will be plotting the omega. So that is our goal. So everybody, could you follow me so far?
Yes.
Yeah. So I mean, just this is the high level idea. Then now I am going in detail in terms of calculation and the circuit. And also I think you have your lab, then design lab. So this knowledge will help you a lot to understand those labs. Okay, so I am stopping this one and then I am taking you there again. Okay, so therefore you see that we are in that slide. So this is the definition: low pass filter, high pass filter, band pass filter, and band stop or notch filter. Okay, now moving forward. So everybody see here the detail about the low pass filter. So this is the low pass filter circuit. So meaning that you have a input and then you have resistance and capacitance. So if you have in the circuit resistance and capacitance, and if you take the output across capacitor, that will behave the low pass filter. I mean, you see that here I have drawn the ideal curve that I was showing you. I showed you in the whiteboard that is the ideal curve, but the actual curve so may look like that. So I am coming that point soon. So everybody say, I said that this is a low pass filter. So how can you prove, how do you understand that this is a low pass filter? That's why. So everybody, let's have a look at its transfer function. And as I said, you have to express your transfer function in terms of omega, because omega involves the frequency. We are looking the frequency variation. Therefore, filter means it's like the frequency response. Everything is in terms of frequency. Okay. So everybody see what will be the output for this circuit V naught T. See, like I have done for you. Everybody see the equation. So V naught T. So definitely this is the input. So input over the impedance, total impedance. You see, this is my input VIT over what is the total impedance? This is R plus for this one on over j omega c. You see phasor form. So I am writing in the phasor form because there you can see the omega. And then what is the impedance of this one? On over omega c. That I am multiplying. So this is my V naught T. And then you see, because V naught here, Vi here, so V naught over Vi. This is actually the H omega. That is my definition of transfer function. So that is H omega, and then you see what I am doing here on over j omega c. This is this one. In this line, again, I simplified something. Everybody see? So it will be the j omega c will be cancelled from numerator denominator. So in the numerator, it will be 1, and in the denominator, on plus this one, j omega c. So now this is my transfer function expression, including the omega. So next time you see in this line, I am just taking its magnitude. I am taking its magnitude. So then H omega 1 over, you see, because this is actually 1 plus j omega CR. This is the rectangular form. What is its magnitude? So root over that 1 square plus that omega c is R square. So this is its magnitude. Now here, by looking this on, you plot. I mean, that I was showing you in the board, this axis omega, and in this axis that magnitude of H omega. Now, everybody look this equation. Look more closely this equation. Now put what I have said, if omega is 0, this means this point in the plot 0. If you put 0 here, then what you are getting? So like 1 over 1. So you are getting H omega 1. So therefore everybody see I have plotted when it is 0, I have plotted it 1. Okay. If omega is infinity, everybody look. If omega is infinity, infinity means very, very large frequency. That is the meaning. So this means the denominator is infinity. So what is the result? 1 over infinity means that will be your 0. That's why you see when it is very high, so I'm assuming that that point is very high, which is equivalent to infinity, it became 0. That is the meaning. And then there is one point here, you see, look this plot. Here, around that point, there is a value which is 0.707. This means 1 over root 2. Like if you have calculator, if you say 1 over root 2, it will give you 0.707, this point, which is of course below 1.0. Now that point is important because corresponding to that point on the curve, there is a frequency which is called omega c. That omega c is called the like cutoff frequency that I was telling you, and I have written it here. Now, what is the meaning? Which one is the cutoff frequency? The transfer function where the value is 0.707, or in other words 1 by root 2, that corresponding frequency is called the cutoff frequency. So that's why here everybody look what I am doing, that at omega c, I mean at that point, magnitude of omega c is 1 over root 2. So this means that now I want to know that what is that value. How do you understand that what is the value of omega c? When it will be 1 over root 2. So that I am doing here. So everybody look. Therefore, this is my transfer function. Look, this 1 over this one. That I am equating with 1 over root 2. And then I will be getting what is the value of omega. That will be this value, omega c. So therefore, look my calculation. So I am just simplifying. I made square on both sides. So it became 2 and then this becomes this one. So finally, you see, I am getting omega c on over RC. Omega c is on over RC. This means that for this circuit, if you know the value of R and then C, whatever it is in microfarad or millifarad, R is ohm or kilo ohm, then on over RC will be cutoff frequency. This point. What is the meaning of the cutoff frequency? Meaning that at that frequency, the value of the transfer function is on over root 2. And so why this point is important? I mean, soon, not today, in hopefully next class, I will be discussing the series resonance, like the parallel resonance. That time we will be noticing that at cutoff frequency, actually circuit power becomes half. That's why it is also called the half power point. So we will be discussing that on later. So for today, you just remember that that point is called the cutoff frequency. So similarly, like this is the low pass filter example, but for high pass, band stop, for each filter, there is a cutoff frequency point. So we will be looking those things. So everybody, do you understand these calculations and plotting this one? Could you follow me?
Yes.
Yeah.
Yeah.
So yes, everybody, like everything is in detail. And then, so have you in any lab, have you already did the filter or still you did not go there? I think.
We did a filter in design with we did a high pass filter, I think.
Okay. So therefore, in the next slide, I am showing you that high pass filter. It will just be exchanged. You see, C will be here and R will be there. And if you take the output across R, that will represent your high pass filter. Therefore, already you did lab. You see, like unfortunately, like our lab and then this course does not match because lab started much early from the second week. In fact, by then we could not cover that. So that's why kind of you have to treat that lab is somewhat independent and then this one. Anyway, so therefore let's have a look the high pass filter. Everybody see the high pass filter diagram. As I said, it is like interchange swiped. If you take the output across R, that will represent the high pass filter. I mean, see the diagram. This is your high pass filter. You see, this is the ideal curve, and then this is the actual curve. This means it is allowing the high pass to flow or to go. So now everybody see for this one again, similar to the previous one, see the calculation. So what will be your transfer function for this one? Here I have written h omega v naught over vi. So because you have to take output across R, that's why here it is R. Because you see that vi over this impedance R plus 1 over j omega c multiplied by R. Therefore, directly in the first line I have written vi is here because vi was there. And then I am simplifying, you see. It was R in the numerator, but this j omega c is going there. So numerator becomes j omega c R over then this one, R plus j omega c R. So now again, I am taking the magnitude of that one, h omega. So what is that one? This one, root over this square, and then in the denominator, root over this square plus 1 square. Now again, the similar way, the previous case, now you plot. When, let me speak a little bit, yes, sorry. Okay, now it is fine. So everybody say, if omega is 0, then put the 0. So omega is 0, then numerator is getting 0. In the denominator, you will have 1. So h omega is 0. Therefore, here you see, At the very beginning, you are getting 0. So therefore, but on the other hand, when it was low pass filter, when it was omega 0, there was value. It was 1. But here you see high pass filter, when omega 0, then definitely transfer function is 0. And then when omega infinity, everybody put omega value infinity. This means both numerator and denominator infinity. So infinity over infinity is 1. So that's why h omega is 1. You see here. That very high value. So I'm assuming this is the high value in ideal case. That's why that point is it is 1. And then now we have to find out this point on the curve, on the actual curve. What is this point? When the value is 1 over root 2 or 0.707, at what point? So that this means this was my transfer function. You see, it is omega c root over e square. So I just wrote omega c RC, and that I am equating with 1 over root 2, this point. So, and then you see, you square both sides, and then you simplify. Again, you are getting the same thing. Omega c is 1 over RC. When omega c is 1 over RC. At that time, you are getting 1 over root 2. So therefore, everybody look, ultimately, if you plug in omega c 1 over RC in the original h omega equation, put this on there. So if you put, look everybody, omega is 1 over RC. So RC cancel, it is getting 1. So in the numerator is 1. And look the denominator, again you are putting omega is 1 over RC. So this means again that is getting 1. So 1 plus 1, 2. So then root 2. So you are getting 1 over root 2. So meaning that your cutoff frequency means that where the value is 0.707, how you will get that? 1 over RC. Therefore, this omega say 1 over RC here and the previous case, it is the same. And it is easy to remember. So everybody, could you follow?
Yes.
Yes.
Yes, right. So great. So now let's move forward. The third category, it is called band pass filter. So band pass, by the definition, as I told you, meaning that you see, I was showing you this graph. Ideally, it will allow to pass a certain band. For example, it will allow only this one, omega 1 and omega 2. Before this one, after this one, it will not allow. So therefore, what is the circuit? This is the circuit. You see, so far we looked RC combination by interchanging low pass, high pass, but band pass, you need the L as well. And then you will be taking the output from here, from R, across the R, and you will be putting LC just in series. Now, if you interchange, like if you give the R here, and if you take the output across LC, that will be your band stop or the notch band. So I am coming that on later. So everybody look, for this circuit, again your goal is the same, find out the transfer function. So therefore look, V naught over Vi, but in this case you are taking output across R, that's why R is here. And then in the denominator, your total impedance. What is the total impedance? This is R plus J for this one, omega L, and for C, minus 1 over omega C. So you already know this format from the impedance calculation. And then again, you express its magnitude. So this is the expression. So R root over this R square plus omega L minus omega C squared. Now again, get some values. We want to plot this on omega versus H omega. If omega is 0, in this equation, everybody put omega 0. So if you put omega 0, then look this one, this is 0, but here it is 1 over 0. So what is 1 over 0? 1 over 0 means it is infinity. So this means ultimately your denominator is infinity. But then something over infinity is 0. Therefore R over infinity, you will get ultimately 0. So that's why you look the plot when omega is 0. the transfer function value is 0. And then see what happens when omega is infinity at very, very high value. So omega is infinity, definitely it is infinity. But this is 1 over infinity, this is 0. But already because it is omega L, so it is infinity. So ultimately your denominator is infinity. So then again R over infinity means 0. That's why you see again at omega infinity value is 0. So therefore at two extremities value is 0. So now what is that point at omega equal to omega naught? You see here at omega naught, because real curve is going in that way. Actual curve is like that. It has a maximum point. It has a maximum point. So that maximum point is definitely 1. So corresponding to that point, I have given a new name, which is omega naught, which is omega naught. Now, what is that value? At omega equal to omega naught, you will be getting that at 1 over root over LC. So how I will get that? H omega is 1. So this means this is your transfer function. You write that point is 1. And then you go ahead. You just square on both sides. Then next time you are getting this line. And then r square getting cancelled. So this one is 0. Again, after making root over, then again you are omitting that 2. And then ultimately you are getting omega naught is 1 over root over LC. So this means when it is 1 over root over LC, at that time the value is maximum. So that's why this point is called the resonant frequency. Resonant frequency, when the value of the transfer function is the maximum. Therefore, for example, in fact, because the value is maximum here, so the signal strength or the signal power is the maximum at this point. Therefore, the real life example, for example, again, you are driving your car and you want to listen a specific band of the radio, and then okay, you switched there, either high pass, low pass, band pass, whatever, and then you want to hear, you want to listen at loud voice, and then what you do, like you tune, right? You control the volume button. Basically, you create this resonance point. You choose this point, and at that time, your voice is the maximum. It is the loud. So that's why this point is called the resonant frequency point. Omega naught is 1 over root over LC. So everybody, do you understand these calculations?
Yes.
Yes. So in this case, and then later in the problem, we will find out what is this point, omega 1 and omega 2. And see that omega and omega 2, actually that corresponds to 0.707. And then later, as I said you, in next class, we will be looking series resonance, parallel resonance. That time, if you calculate the power for this circuit at this point and this point, then you will be getting exactly the half power. For example, at omega naught 0, at this point, if the power is 100 watt, just an example, at this point and at this point, you will be getting 50 watt, half of the power. That is pretty interesting. I mean, it is not like that this point is half. This is not 0.5. But if you calculate the power, you will be getting exactly the half power. Accordingly, this omega 1 and omega 2 frequency are called half power frequency. This is called the resonant frequency or the cutoff frequency, but that omega 1 and omega 2 are called the half power frequency or half power point, because power will be exactly half, although the transfer function value is 0.707. So what is the reason? Because in any circuit, power is not a linear function. Power is non-linear. Because, for example, for R, if you know the current, what is the power? I square R. Or if you know the voltage, V square over R. So you all know that I square and then V square, those are non-linear. Because of that non-linearity, power at this point or at this point will be half. Although it is the maximum here, but at the 0.707 point, power will be half. So next time we will be looking that on. Okay, so then moving forward, the other category, you see, band stop. Like I was showing you the picture ideally. Nothing will be passed at this point. Everything will be blocked between omega and omega 2, but it will be allowed before this point and after this point. So how does the circuit look like? You see, as I told you, then again, like R will be here, and you have to take the voltage across both, across the series combination of L and C. Only then you will be getting the band stop, that characteristics. So therefore here everybody, once again, calculate your transfer function, H omega. That H omega is V naught over Vi. Again the same thing. Now everybody look, in this case, you are taking the output across the series combination of L and C. Accordingly, here I have written its impedance. So this means J omega L minus 1 over omega C. And in the denominator, the whole combination, R plus J omega L minus 1 over omega C. And then again, you find out the transfer function, H omega, its magnitude. And then, so numerator is root over this squared, and in the denominator, R squared plus this square. And then now again, the similar to other filters, you plot those points. What is 0, what is at infinity, and what is the value at omega naught. So everybody look, you put omega equal to 0. So this means what you are getting, if you put omega 0, it will be infinity, because 1 over 0 is infinity. And then what will happen in the denominator? That will also be infinity. So therefore, infinity over infinity, value will be 1. So that's why you see at the 0 point, you are getting value 1. And then come back, what will happen at omega equal to infinity? So omega infinity, definitely it is getting infinity, and denominator is also getting your infinity. So infinity over infinity, that is also the 1. So that's why at very high value, you see, I have shown the value is 1. Now, I am interested to find out this frequency. What is the value? How I can get that on? So therefore that omega naught, sorry, this one, at omega equal to omega naught, again you will be getting 1 over root over LC. I mean that we concluded here. So meaning that when omega equal to omega naught, 1 over root over LC, at that time transfer function value is 0, this one. So for that on, what I am doing, this is my transfer function. I am equating with 0 because I want to get this point. So then, and then you see, I have changed the symbol of omega, omega. I have expressed in omega naught because at this point, the value is 0. That's why. So then again, you see, squaring on both sides, and then you are getting this one. Ultimately, you see, from calculation, you are getting omega naught 1 over root over LC. In this case, this is that resonant frequency at which the value of transfer function is 0. And this is for that band stop filter. And sometimes because it looks like the notch, it looks like a hole, also it is called the notch filter. So everybody, could you follow so far?
Yes.
Yes. Okay, great. So then again, I mean, after the class, we will be looking because these slides will be available. Now let's go to a specific problem. You see, everybody look, there is a problem. Determine what type of filter is shown in the following figure, and then calculate the corner or cutoff frequency. That cutoff frequency, sometimes it is called the corner frequency as well. That's why. This means the omega C value. And then take R 2 kilo ohm, L 2 Henry, and C 2 microfarad. So therefore, everybody say this circuit I have not shown before so far. You see here it is in series. Then this one also in series. And then in the high pass filter, it was the combination of RC. And in the low pass filter, it was also the combination of RC. So therefore, but then here I have made a parallel combination. I mean, those RLC are there, but R and C in parallel. So therefore, by looking, you cannot tell what is the type. So, but if you can calculate its H omega, and then if you plot the curve, if you look the curve, then you can tell what is the type. That is the question. Determine what type of filter is shown in the following figure. And then calculate its corner frequency given the values. So therefore everybody, so what you have to do? What you have to do for this circuit? You have to find out the transfer function. And the very first task, find out the voltage across the capacitor. That is your very first task. This means that for this circuit, first find out what is the total impedance, then find out the total current, and then find out what current is flowing through C, and then multiply that current by its respective impedance. That is your V0. And then you can make a relationship between V0 and Vi in terms of the H omega. And then by looking that H omega, you can determine what is the type, whether it is low pass or high pass or band pass or band stop, either of those, any of those categories. That is the question. So therefore, everybody see, I am calculating it here. So first, that is my circuit. First, you see what I am doing. I mean, I just wrote down H omega V0 over Vi. And then I have written down, you see, V0 means this one. IC means the current that will be flowing through this one, multiplied by 1 over j omega C. Now, what is the IC? So to do that, first you see what I have written here. First, I am calculating the GT, total impedance for this circuit. What is the total impedance? You see, these two are in parallel. So R parallel 1 over j omega C. And then this one, j omega L. So this is your GT. And then you have to simplify. What I have done, like R parallel 1 over j omega C. For this one, I just said, okay, replace momentarily S equal to j omega. Just I am taking the help of the Laplace to calculate. But at the end, definitely I have to put the S equal to j omega because I am doing the frequency response. I want to determine the type of filter. Definitely, it must be related to omega. But for simplicity purpose, here I am just replacing j omega by S. So that's why when I am making the parallel of R and C, I wrote in that way R parallel 1 over j omega C. But you see j omega is S, so in the format of S. So this is the format. Okay, and then then I am writing the IT. IT is VI over GT. So your IT will be here, total current. And then IT, what is VI, what is GT? GT means this parallel combination, which is this one, R over 1 plus RSC. And for this one, it is J omega L. I mean, originally I wrote, but then I just wrote SL so that I can calculate in terms of S, Laplace operator. And then that is my IT. And once I got the IT, my goal is to find out this current. You see that I have written here that V0 is IC, what current is flowing through C multiplied by 1 over SC or 1 over j omega C. So therefore I am applying that current divider rule here, IC. So this means IC means total current, IT, multiplied by R divided by R plus 1 over SC or 1 over j omega C. So I am applying the current divider rule here, and then I got this one. I expressed in that format. And then in the IC, I am getting IT, but this is my IT. I am substituting IT value there. So finally, I am getting this one and in that format. So my IC is VI multiplied by RSC and divided by this one. And then this is my IC. You substitute this IC in that equation, which is my V naught, because actually I am calculating the V naught. So what I am getting this one. So sorry, after simplification, finally I am getting this one. So here you can see the transfer function V naught over Vi. You will be getting V naught over Vi. So therefore, in the next slide, I am writing that one. H omega V naught over Vi R over this one. I mean, so ultimately this one. Everybody, could you follow these calculations? This is just the basic circuit that we have done a lot, similar circuit. Everybody, could you follow?
Yes.
Yeah. I mean, you may not necessarily do in that way. Your goal is to calculate the V naught. Therefore, to do that, whatever you need, you do. So what I did, I mean, in summary, that I first found out the total impedance, and then I found out the total current here. And then I calculated the current flowing through, say, and I multiplied by its impedance. And then I have reached this line finally. And then from there, I am going, because V naught over Vi, that is your transfer function, that I have written down here, V naught over Vi. So therefore, everybody say V naught over Vi. But in the denominator, you look, there is S square. S square RLC plus SL plus R. Now, as you see that I simplified, I started using the Laplace operator, but then I have to go back to omega domain. I have to express in terms of frequency. That's why, again, I am going back. I am substituting S equal to J omega. This means here AC square is minus omega square, because J square is minus 1. So look, H omega, this is R. In the denominator, AC square is getting minus omega square. So minus omega square RLC is J omega L, and then this R as it is. Now this is my expression. This is my expression of H. So therefore, because my goal, the question was determine the type of the filter, what type of filter that represents. So that's why, you see, again, I have to find out what is its magnitude. So that I am doing. You see, in the denominator, it has both real component and then imaginary component. So therefore, R minus omega square RLC, this is the real part, and then J omega L is the imaginary part. So accordingly, you see that I am finding its magnitude. So that's why here R minus this one, omega square RLC, that whole square, plus this omega L square. Now, with the help of this one, you say, everybody plot, put the omega is 0, then what? So if you put omega is 0 here, then this is 0. So it is becoming R squared. This is 0. So after root R. So R over R is, you are getting 1. So therefore, what you are getting, that when omega is 0, at that time you are getting H omega 1. And then what is the value of infinity? If omega is infinity, put omega infinity here. So therefore you are getting this one is infinity. So R over infinity means that is 0. So therefore, what does that represent? At the beginning you are getting 1, and at high frequency you are getting 0. Definitely that is the low pass filter. But then I said this is a second order low pass filter, because it was like omega squared. That's why it is a actually low pass filter. So that was the question. So therefore you see, although it looks like that, but actually it is representing the low pass filter that we look at the beginning, low pass filter. So what is the characteristics? At 0, it is value is 1, and then after that value is infinity. So that is the meaning. So therefore we got the result that that circuit, actually it is a second order low pass filter. Now the second question was, what is the calculate the cutoff or corner frequency? How you will calculate the corner frequency or the cutoff frequency? So therefore here I think I have written down the answer. So if we need to use a calculator, omega is 742 radian per second. Now, how you will get?
I don't even know how to put this.
Hello?
But see, in 20.
Hello, so does anybody say anything? Okay. So everybody say, what is the cutoff or corner frequency? So what is the definition we looked? The value of the transfer function at that point or at that frequency, it will be 1 over root 2. You see that originally when we did the cutoff frequency, the value of the transfer function will be 0.707 or 1 over root 2. So the same thing we have to do it here. I am writing that transfer function, you see this one, r over this one, it is 1 over root 2. And meaning that I have changed the symbol of omega omega by omega c. So therefore everybody say, finally, you will be getting omega c 742 radian per second. Now, you see, I have said that the detailed calculation omega c is shown in the next page. Can you see the format of the equation? Because it is omega c squared, and then again you are making squared. So it is getting omega c power fourth power it is getting. So although you know the value of RL and C, those values were given, RLC values were given, but because you have to find out the omega, you have to find out the omega, but it is getting omega c fourth power. So that's why immediately you will not be getting, and then there is omega c squared here. It is getting kind of the quadratic format, quadratic equation. So that's why easily you will not get this one. So you have to look the detailed calculation. So therefore, from this one, everybody look, from this one, I am simplifying. Here is the detailed calculation. I mean, this is the start point of this line, the last line. Keep in mind. So I'm multiplying 2r square and then this one. That I am doing. Everybody, could you follow me what I am doing?
Yes.
Yeah. So my goal is to, I mean, there I have ended. I just wrote down the answer. I mean, I am done there. But how I got that on that I am showing you again detailed calculation, because you see the complexity of the equation. It is like r square minus 2 r omega c to the power 4 r square l square c square. In that way everything is coming. That's why it is not straightforward. That's why I am showing the detailed calculation. So therefore you see, just then I am simplifying, you will see calculation. And I already substitute the value of RL and C. I think from here, you see, you cannot see RLC anymore. I have put, and then I have simplified in that way. This expression, it was 10 to the power minus 6, you know. So that's why I have expressed omega c over 10 to the power 3 and then squared, because it was omega c squared. So why I did that one? I said assuming that omega c is in kiloradian per second, because I have to find out that omega c unit will be radian per second. But I said, okay, let's assume omega c is kiloradian per second. If I do that, I mean, I assume that just looking this one, so that omega c over 10 to the power 3, I can say that this is here in kiloradian per second. So that's why you see this 2 is this 2, 1 minus 4. Just I wrote omega c squared because my omega c is in kiloradian per second. And then here also, instead of, I want to avoid this calculation, that's why omega c squared. And then again you are expressing, you see, finally, can you remember this one? Which equation I have used? So that quadratic equation, like x equal to that minus b plus minus root over b square minus 4ac over 2a. Everybody, do you understand what I'm saying? The solution for a quadratic equation, that format. This is my quadratic equation, but it is omega c 4th power minus 7 omega c square. So I am assuming I am treating that omega c square is my x. So therefore ax square minus bx minus c in that format. So that's why I am writing omega c squared is, everybody look, minus b. This means minus minus plus 7 plus minus root over b square. What is my b? Minus 7, 49. Then minus 4ac. What is my a? 16. What is my c? Minus 1. So I got this one. Divide by 2a. This one. So therefore, I got omega c squared this one. And then omega c square has two value. One value is 0.5509. Other value is minus. But omega c squared cannot be minus. So this is not my solution. Finally, I got omega c is 742 radian per second or 0.742 kiloradian per second. So everybody, do you understand?
Yes.
Yeah, I mean, this is just the long calculation. You just need to be a little bit patient. That's why I showed that how I got that on. I wrote that on that result omega c here, but then I am showing you the detailed calculation in the next page, or this page, and how it came. And then, I mean, at your home, at your free time, everybody again, once again, very carefully, with patience, look line by line, then you will be getting it, like how I did that. So therefore, for the problem, the question was, okay, what is the type of the filter? So we concluded that although it looks like the parallel combination, but ultimately it's a second order low pass filter because it is a second order circuit. Accordingly, it's a second order low pass filter. And then we calculated the corner or cutoff frequency. That's all. Okay, so therefore we just started frequency response today. We understood the type of the filters, and then next class we will be looking some other important concept in frequency response, which is called the resonance. And there is series resonance, parallel resonance. And then I think those concepts will cover a lot to your design and some of the labs. Okay, so is everybody fine? Do you have any questions, comments?
Yeah, I had a question about the homework. I was doing like questions 2, 3, 4, and 6 kind of have crazy numbers when I get to the transfer function.
Okay.
So can I just plug in can I go put that in a calculator and just get the partial fractions out of that? Because I
Yeah,
don't.
yeah, you could, you could do. Yeah.
All right.
Yeah, you could do that. Yeah.
Okay, thank you.
Okay. So, is there any other questions, comments from anybody?